Here we are in section 5.3, and actually we get into the Riemann sums and um, the integration and the much easier way to find the area, and even better, it's the actual area. It's not just an approximation as we have done in the last couple of weeks. And so we begin with how can we convert a summation into a um, an integral to actually help us to solve these problems. Well, there is a situation. If we look at the limit as each partition, the width of each partition approaches zero. Remember I said a couple of weeks ago that the partitions or the rectangles are going to get infinitely smaller and smaller. So that's what this is saying. The limit as the width of the partition gets closer and closer to zero of k equals 1 to n of 7 ck raised to the 7th power of delta x sub k. A whole bunch of stuff. But realize we don't want to go through this whole mess each and every time. First of all, it would be impossible because we have to get this infinitely small, and we're just not going to take the time. And we're going from the partition from 2 to 9. Now realize we are asked to write this as what is called a definite integral. What we have used up until now have been called indefinite integrals, and indefinite integrals we always have to put those plus c's. Now we don't need to worry about those so much. Now 1 and 2 we're just asked to express it. We're not asked to go ahead and do the calculation, but what we need to do is we need to know how do we convert from this, all this information, into something else, which is actually considerably smaller. What it is, we start with our sigma. Now notice this is a sigma, so is this. There is some method to math madness. And then this becomes, this remains a 7. This c sub k, this is actually, we're going to replace that with an x, or whatever variable we need or want to use. Most commonly it's x. So this would be x to the 7th power. Now notice this is delta of x sub k, so that's going to be dx. Remember I said the dx is important. It's still, we generally know what we mean if it's not here, but we still need to put it there. And then how do we do the 2 and the 9? Well, we put the 2 down here, we put the 9 up there, and we're done. We are basically done. We have converted this big long mess into something this small. Once again, what this proves is this proves mathematicians don't really like to do a whole lot of writing. Number 2, the limit as the width of the partition approaches 0 of the segment going from 1 to n of the sine of c of k, c sub k, of delta x sub k, and the partition is from negative pi over 3 to 0. So this limit business, all this is summed up with that sigma right there. We're going to do the sine of, well, we don't do c sub k, we do the sine of whatever variable. I'm going to use x because it's most commonly x. And then this delta here turns into a dx. And then we're going to go from negative pi over 3, so I'm going to put the negative pi over 3 here at the bottom and 0 at the top. And understand that it is very, very important to realize which one goes here and which one goes here. The first one goes here, the last one goes up here. You just have to understand that because it does make a big difference, and in fact we're going to see how that makes a difference in these next couple of problems. Example number 3. Example number 3, we are told the integral from negative 4 to negative 1 of g of t dt is equal to negative 4. we are asked to find what would be the integral of from -4 to -1 of g of x over -4 dx, and what would be the integral from -1 to -4 of negative g of t dt. Notice these variables are just getting interchanged, and that's perfectly fine. If I wanted to put a p, I could put g of p and dp here, or whatever goes here. Okay, now, for this particular one, what we need to realize is this is just a funny looking 1/4, or actually funny looking -1/4. And much like when we had the summation, if we have a number, we can pull it out front, and that's going to be the same thing. -1/4, the integral from -4 to -1 of g of x dx. Well, the integral from -4 to -1 of g of t dt is -4. Well, the integral from -4 to -1 of g of x dx is going to be exactly the same. So this becomes -1/4 times -4. Or this all equals out to be the number 1. Now if we notice the difference here compared to the first one is this is just reverse. Well, how we affect that, or how that affects us, is to get this to the -4 and -1, which is what we need, we are going to take the negative of that. Okay, to get, if these are exact reverse of what we need, then we just take the negative of it, and we will, and then invert those two numbers. So the negative, and then I can invert these to -4, -1 of negative gt. Well, it's still not the same because we have this negative, so we need to bring this negative out front here. So it ends up equaling the integral from -4 to -1 of g of t dt. Now, the integral of -4 to -1 of g of t dt, according to our problem, is equal to -4. So the answer is -4. That whole mess to end up with what we had at the very beginning. Example 4. Okay, we're told h is continuous. That is important because we need to do some combinations here. So to go from -4 to 5 of h of x dx is equal to 3. We also know that the integral from 5 to 9 of h of x dx equals -8. Now the reason we need to know that h, well, not yet. What is the integral from -4 to 9 of h of t dt? And what would be the integral from 9 to -4 of h of t dt? Okay, now realize these are just inverses of each other. You know, the only thing different between this one and this one are these two are switched. So that means once we find this answer, to find the answer here, all we have to do is negate it. We've got it. So that's not going to be too hard. But the first question we have to look at is, okay, what is this? Now this is where the fact that h is continuous becomes very important, because we have from -4 to 5, and then we have from 5 to 9. So if, you know, it would make sense that, okay, we should be able to split this up. We can start at -4 and go to 5. And then we can add on to that from 5 to 9. Because, see, notice this goes from -4 to 5, and then we just pick back up at 5 and go all the way up to 9. According to what we know, from the integral from -4 to 5 of ht dt is equal to 3, and the integral from 5 to 9 of ht dt, h of t dt, is -8. And 3 plus -8 equals -5. So that's what that equals. Now, to show all this work, even though we know, the our inverses, we better end up with a 5, a positive 5. Realize all we have to do is take the negative of, from negative 4 to 9, of h of t dt. That's the negative of, okay, we just got done determining that the integral from negative 4 to 9 is negative 5. So negative 5 equals 5. That's a very, very simple way to get to that answer. If you really wanted to, you could say, okay, I'm going to go from 9 to 5, and then 5 to negative 4, and then I would have to find the negatives of each one of those, and would be the negatives of each one of these, and add those together. Or you can just say, well, I already know this answer here, the negative 4 to 9, so why not just take the negative of that? Once again, it's entirely up to you, but I would certainly do it in that fashion. Examples 5 and 6 go back to the last couple of weeks and how this would look compared to what we did last week. You get 0 to 4 of 10x dx. Now, the only difference here is the fact that we're going to find the actual area using geometry. God forbid that we'd have to use geometry. Now what this says is we're going to go from 0 to 4. And we need to graph 10x. Well, 10x would be 0 is a straight line all the way up to 40. And so from 0 to 4, we've got this right here, which is a triangle. The area of that triangle is 1/2 base. Well, the base is 4, and the height is 40. 1/2 times 4 times 40 is 80. Now that's the area using the geometry. Let's actually, we're not quite ready to do this. We'll come back to this. How do we find the integral here? And what do we do with these additional numbers, the 0 and the 4? We'll deal with those in just a second, but we will come back to it when the time comes. Example 6. Example 6, let's see, we want to go from negative 1 to 9, and it's the absolute value of x dx. Okay, so to draw this, I have to go from negative 1 all the way up to 9, and absolute value, remember, has a V shape. It looks something like this. Now realize what we're going to have to do is we're going to have to find the area of two triangles, because we have two different triangles. So I'm going to take this one first, call that area 1. So that would be 1/2, the base is 1, and the height is 1. So this all equals 1/2. For this triangle, we get 1/2 times the base, which is 9, times the height, which is 9. And so this would be 81/2. Add those together, we get 82/2, which is equal to 41. So just using geometry, we've determined that the area of this is 41. Now, I could go and do the integral of this, but well, we pretty well need to do it. So what I'm going to do now is I'm going to go into how can we use definite integrals to find the areas. So let's go back up to here to number 5. Okay. We know how to take the integral of 10x. That's the antiderivative. So this would become 10x squared over 2. Normally we'd put plus c, but since we've got numbers, we don't need the plus c. This actually helps us to determine, what else, well, everything that we need. Now, we have to realize that we are eventually going to be evaluating this at the values from 0 to 4. Now, you've seen this notation. I've used this notation before. But now, this is where I get it from. It's the fact that we're going to evaluate this from 0 to 4. So this becomes 5x squared, and I'm going to evaluate it from 0 to 4. Now, what it means to evaluate it from 0 to 4, that means plug this top number in first. So we're going to get 5 times 4 squared. Plug it in for the x. 5 times 4 squared. 4 squared is 16. Then it's minus, plugging this value in, minus 5 times 0, or minus 0. And so we get 5 times 16, which is 80. Notice those two are the same. And as I've been saying in the past, integrals are a whole lot easier than drawing the graph and trying to figure out, areas of rectangles or areas of triangles or whatever. Now, number 6 causes a little bit of a problem because we have that absolute value. So what we need to do whenever we have an absolute value is we need to split it up at the v point. Okay? So, with that in mind, let's look at what we can get here. I know I'm going to go from -1 to 0. And I look at what is this line right here? What is the equation of that line from -1 to 0? Well, that is -x. And it has to be dx. Then we're going to add, what is it from here? Okay, this is going to go from 0 to 9. The equation of this line would be positive x dx. And so that's how I split up absolute values. I look at where's the v point, and I treat them as two separate problems. And I'm going to have to determine what is the equation of this other line, and this line for that matter. So let's look at what happens here. Take the integral of this. We get -x squared over 2, evaluated from -1 to 0. Plus, take the integral of this, it's x squared over 2, evaluated from 0 to 9. Okay, so this will give us, plugging in 0, -0 squared over 2, that's 0, right? Minus, because it's always this plugged in minus this plugged in. So minus, okay. -1 squared is a positive 1, but this becomes -1/2. So minus a -1/2. That's what this part of it equals. Plus, now I need to do the same thing here. Plug in the 9. 9 squared is 81 over 2. Minus, plugging in the 0. 0 squared over 2 is 0. And notice this turns into a plus. We get 1/2 plus 81/2, which is 82/2, which equals 41. Once again, we get the exact same area. So at least with these examples, you should feel pretty confident that, at least for these two, this does work. As it turns out, this works all the time. So, with that in mind, let's look at example number 7. We are asked to evaluate from 0 to 1/9 of t squared dt, and evaluate what it is. Well, first thing we have to do is find the integral of this. This is t cubed over 3. We're going to evaluate that from 0 to 1/9, which will equal 1/9 cubed over 3 minus, I'm just plugging in the 1/9, minus 0 cubed over 3. Well, zeros are usually nice to work with. 1/9 cubed. is 1 over 700. Can't remember right offhand. But realize whatever this is over 3 ends up equaling 1 over 2,187 minus 0. So our final answer is 1 over 2,187. And that shouldn't be a big surprise if we look at the graph of t squared. Just going to do a very quick one. T squared like that. And we're going from 0 to 1/9. Well, 1/9 is about right here if this is 1/1. It's not much area down here. In fact, it's 1 over 2,187 units. Not much at all. Number 8 provides a little interesting exercise. Going from 1 to 7 of 6 dx. Well, the antiderivative of 6 is 6x. We're going to evaluate from 1 to 7. Plugging in 6 times 7 minus 6 times 1. 6 times 7 is 42. 42 minus 6 is 36. Now let's look at what this means. Suppose we were drawing this. 6. Well, 6 is just a horizontal line. Here it's 6. And we're going from 1 to 7. This isn't too difficult. What's its base? This is a rectangle here. Its base is 6. Its height is 6. 6 times 6 is 36. It makes sense here. Here it is the actual value. Here, you know, it's reasonable. We're on number 7, we're not absolutely 100% sure that's the answer, but it certainly is reasonable. Once again, I say that so that you realize this is a huge use of integration to find the area between a curve and the x-axis. Okay, number 9. Number 9 says use a definite integral to from over the interval 0 to b of y equals 10x. Okay, so we're going to do the integral going from 0 to b. It's okay to have variables here. You may not like it, but you have to be able to deal with it. Of 10x, and you always have to remember the dx, because I've shown where if it's a t here and you put dx, it has a whole different meaning, and we'll look at that a little bit later, but I don't want to confuse you right now. But right now, we need to be very careful with that. Okay, well, this means we need to take the integral. That's 10x squared over 2. We're going to evaluate that from 0 to b. Don't have this magically disappear and then reappear, because I don't like this either. I find this as being, you know, extra writing. But we need to simplify this now to 5x squared and go from 0 to b. Like I said, don't have it magically disappear here and reappear here. Just a word of warning. Now we can actually plug these values in. We get 5b squared minus, because we plug the b into here, minus, plugging 0 in here, we get 5 times 0 squared. And so, of course, this would be 5b squared minus 0, or just simply 5b squared. Okay, and since this is still definite, this is still a definite integral, we have the start and the beginning, or the start and the end, we don't need a plus c. And in fact, if you put a plus c, it's technically not incorrect, but I'm going to count it incorrect, because c's in this case end up being zeros, because we've got all the information that we need already. Okay. (10) and 11 ask for the average value. Well, the average value, what we can do is we can find the volume and then divide by how many units we've gone across so that we get the average. Because it's, in essence, the same thing. It's really hard to explain, even in person, why this is so, but this is how you find the average value of a function, is to take the integral and then divide by how many units you've gone through. Okay, so we have f of x is equal to negative 2x plus 2, and we're going from negative 2 to 1. So we will go from negative 2 to 1 of negative 2x plus 2 dx. We can now take the integral of this, so this would be negative 2x squared over 2 plus 2x evaluated from negative 2 to 1. Cleaning this up before we start plugging it in, negative x squared plus 2x evaluating from negative 2 to 1. So let's see what we get here. We plug in the 1 here, we get negative 1 squared plus 2 times 1 minus the whole thing here. Plugging in negative 2, it's a negative 2 squared plus 2 times negative 2. And you have to be very careful when you subtract this whole thing. Okay? Continuing, this would equal, okay, negative 1 squared is negative 1. 2 times 1 is 2 minus, okay, negative 2 squared is 4, but that becomes a negative 4 plus 2 times negative 2 is negative 4. And so this equals negative 1 plus 2 is 1. 1 minus a negative 8 gives a positive 9. So that's the total area. That's also what we can think of is this is in essence the summation of all the heights through this whole line. You know, if we look at the first one, we would end up with 6. And then we would end up with 5.99999, then 5.99998, and so on and so forth. And eventually we get down all the way down to 0. So the question is, what's the average height? Well, since the first height is 6 and we go down to 0, it can never be 9. But we're asking, well, what's the average height? Well, we realize we went over 3 units, so the average height would be 3 units high. Now this should not take too much disbelief, because if we went from 6 to 0 over 3 units, and it doesn't matter where it's at, you know, if it's between negative 2 and 1 or 0 and 3 or whatever, if we go from negative 6 to 0, you know, and since this is a straight line, the average would be right in the middle, which happens to be at the value of 3. And so that's what we're saying here. The average height here is 3. Now, number 10 is not too difficult to see. Number 11, on the other hand, may be a different story. Number 11. Number 11 is f of x equals 6 minus the absolute value of x, and we're going from negative 6 to 6. Now here, the very first thing we have to do is determine where's the v. Where does the v occur? Because that will play a big part. And it shouldn't take too long to realize it occurs right at 0, 0. Just happens to go back 6 this way and 6 this way. Now let's just use this. I know the average height on this much of it is going to be 3, because this goes all the way up to 6. And the average height on this one should be 3 also. So what should the average height be of both of them? It should still be 3. But let's make sure that all works out. Now notice what I had to do this so that I can split this up, because I'm going to go from negative 6 to 0 of this line right here. Well, this line would be 6 minus x. No, this is not 6 minus x. That would be blah, blah, blah. Wow, this is just minus x. Yeah. Oh, my problem is I've got my graph wrong. Oops. Okay, this is making a whole lot more sense. The v still occurs at 0, but now my height is quite a bit different. My height here, the average would be at 9 and 9. So overall, the average better be 9. Better thinking, I hope. We'll deal with it in a second. Okay, so yes, this is 6 minus x, and then we're going to go from 0 to 6. The remainder of it is going to be 6 plus x, because that's what that line is there. Ooh, I forgot the dx. Okay, so take the definite integral of this. This is 6x minus x squared over 2, and I'm going to evaluate that from negative 6 to 0. Then take the definite integral of this is 6x minus, plus x squared over 2, and that's going to be from 0 to 6. And then we're just going to add them. So, what does this whole mess equal? Okay, plugging in 0, I get 6 times 0 minus 0 squared over 2, minus the whole thing. Plugging in negative 6, I get 6 times negative 6 minus negative 6 squared over 2, plus. Okay, plug in 6 here, so it'll be 6 times 6 plus 6 squared over 2, and then hopefully it's real easy, minus 6 times 0 plus 0 squared over 2 is 0. It's going to be minus 0 out here. I don't really like doing that this early in a concept, but I'm just out of room. Okay, so this all becomes 0, so that's no problem. So I'll get negative, and then this becomes negative 36 minus 18, because negative 6 squared is 36, 36 squared is 18, and it's minus that. Plus, okay, 6 times 6 is 36, plus 6 squared is 36 over 2 is 18. So, let's see, negative 36 minus 18 is negative 54. Negative negative 54 is 54, plus the 54 that this equals out to be, and that is 108. But that is the total sum of all the heights. We want to know what is the average height. Well, we covered 12 units. So what we need to do is we need to take 108, divide by 12, and hopefully this gives us, what, 9? 108 divided by 12 is indeed 9, which, isn't that what I just got done saying? The average height would be, here would be 9, the average height here would be 9, overall the average height would be 9. So it works out very nice. And I'm just confirmed. Final example, number 12. It says, complete the definite integral as the limit of Riemann sums. No. What we're going to do is we're going to just complete the definite integral. And if there were more problems for this, which I'm thinking there might have been, we're only going to go to 12. So example number 12 is our final problem. And so I will adjust any homework if necessary. So I'm going to take, let's see, this becomes 5x squared over 2 minus x, and I'm going to evaluate that from 1 to 0. And so I get 5 times 0 squared over 2 minus 0 minus the whole thing, plugging in 1, it's 5 times 1 squared over 2 minus 1. And so all of this becomes 0. You know, that's why zeros, most of the time, everything turns into 0. So that works out nice. 0. So I get negative, whatever that is. 5 times 1 squared is 5. 5 over 2 minus 1. This becomes negative. Well, 5 halves minus 1 is 3 halves. And negative 3 halves is the final answer. And like I said, I will adjust, if necessary, I will adjust any of the